Okay, so we have a problem here where blood is flowing through an artery at some speed. Actually, the speed is dependent upon how far the blood happens to be from the center of the artery. So capital R is the radius of the artery, and little r is a value that's dependent, how far away from the artery you are. Now, if you're wondering, wait, why would blood in the middle of the artery flow faster or slower than blood on the outside of the artery? It has to do with something called surface tension. Some of you have taken chemistry, and one of the things you used in chemistry is you used a little pipette, and that water just kind of stays in there. Or perhaps you probably talked about something like a pipette or the big long tube, and I can't remember what that's called right off the top of my head. But the water drains through it very, very slowly. Or alternatively, perhaps you saw water getting sprinkled along a little metal ring, and you'll notice the water continues to fall even though gravity would want it to fall down. Same thing, why does that drop hang in the faucet? It has to do with surface tension. So the closer it is to the outside of the ring, the slower it's actually going to move. And so you can see that very easily. If little r is close to r squared, then the speed's going to be slower. In fact, all the way down to 0. So now we're asked what happens to the speed when we give a drug that's going to cause the artery to dilate. So the first thing we do is we have a function here. S is a function of capital R in this case, since we're allowing little r to be constant, and then capital R itself actually varies. So we're asked to figure out how does the speed change. So we take our equation, S equals c times r squared minus little r squared, and we're going to differentiate with respect to capital R. So c is a constant, so derivative of distribute over that sum. Derivative of r would be 2r, and in this case little r squared is a constant. You're saying the same place in the artery, so that's minus 0. So S is 2CR. C is a constant. Now we want to find how the speed changes with respect to time. So we know that S is related to R, so we want to find ds dt. Well, by the chain rule, ds dt is ds dr, which we've now just found, 2cr, times dr dt. So now it's just a matter of plugging in what we know. Okay. So ds dr is 2cr times dr dt, which we have right over here. So 2cr times dr dt. And then we start working on that, plugging in everything that's given to us. 2 times c, which is 1.76 times 10 to the 5th. R, which is 1.2 times 10 to the negative 2nd. And finally, dr dt, which was 10 to the negative 5th. And now we quickly go to a calculator, or work that out by hand if you want to, and figure this out. And so doing so gives us an answer of 0.02112, and this would probably be centimeters per second. Okay, so here we didn't even need to know what our actual position was. The actual increase would have to do anywhere. And so wait a minute, if it's on the artery, wouldn't it be having a velocity of 0? Well, the artery expanded, so now it's actually further away from the outside of the artery. Okay. So here's an example where we have to make direct use of the chain rule to figure that out.